Characterizing glass evidence. So these are different ways that you can tell, that you can characterize your glass evidence. So you can tell what kind of glass it is you're dealing with or where that glass might have come from based on its properties. And we'll look at different properties of glass to get there. So we talked about density as being an inherent property of matter. It's how much mass you have packed into a given space. Things that are less dense will float. So if you have something that is less dense than water, it'll float on water. So we can exploit this property of density and do a float test. What you'll do is you'll take a liquid vat of these two chemicals, bromoform and bromobenzene. These have a known refractive index each. Your standard reference sample will be submerged, and then the ratio of bromoform and bromobenzene, which again have documented refractive indices of their own, will be adjusted until the standard reference sample floats in the middle. So if you have a known amount of one chemical here and a known amount of the other chemical here, and your piece of evidence can float in the middle, you know that its density is going to be somewhere between them, and you can calculate its refractive index that way. The refractive indexes we'll see is the ratio, is how much light slows down when it goes through something. So you will repeat this procedure for the evidence glass, and if the ratio of bromoform to bromobenzene was the same for the standard reference sample as for the evidence, it can be a match. It is not a definite match. You can have that piece of glass that'll match that density from a whole slew of other sources potentially. Only really specific individual handcrafted types of glasses are going to be definitive types of tests in this way. The sensitivity, basically how precise this technique is, comes to within 0.0003 grams per milliliter variation in normal glass. That's enough so that normal variations between one pane of glass and another pane made by the same manufacturer or it comes out of the same plant will still be ruled as basically the same thing. So remember that glass is a pretty heterogeneous hodgepodge of different materials that are going to have more or less even distribution, but one little chunk of glass is going to be a little different than another little chunk of glass at a molecular level. If your test is super precise, you might be able to detect those differences, those very, very, very subtle differences, and you'll end up coming up with a false negative. Your technique will think that these two things are actually from different sources when they're not. It's important that your technique isn't too sensitive for what you're handling, and this is not. I mentioned before the refractive index and how it is the bending of a light wave as it goes through a different surface. The index is just a ratio of that refractive change. So light is traveling at one speed through air, it hits water, it slows down. When it slows down, it bends. So you're really comparing speeds, and that's going to be reflected in the angle of refraction. Water at room temperature's refractive index is 1.333. If you have a refractive index that's higher than that, you're going to have more refraction. If it's less than that, you're going to have less refraction. This is tabulated using a type of light called sodium D light. If you've ever gone to like the airport or something and seen those weird orangey sort of lights that they have lining the roadways, that's sodium light. So the thing that we're interested in about that sodium light is that it is emitted at a really, really, really constant predictable wavelength of 589.3 nanometers. That's distance between those peaks in the wavelength. The refractive index can be determined for another piece of glass also by the immersion method. So the first method, you were immersing your glass into a solution. But in this case, what you're going to do is submerge it inside of a special chamber that's usually has silicone oil in it. The refractive index of silicone oil is known and very constant. You're going to shine this also very known and constant sodium D light through the silicone oil and at the glass that you're going to submerge in the silicone oil. Now, what you'll see when you look at it without any kind of tweaking is that the glass is going to have this weird sort of glowy outline to it, and that's referred to as the Beck line. The Beck line is basically an artifact of refraction. So as long as the refractive index is different between the two solutions, you're going to have a Beck line. By changing the temperature of the silicone oil, you're actually going to change the refractive index a little bit, also in a predictable, known way based on how much you increase the temperature. Remember, the molecules, when you increase the temperature, are going to have more energy, and so since the molecules are moving differently, it's going to refract light differently. When you adjust the temperature at a very slow, constant rate, and you examine an image of it through the microscope, that image is going to be transmitted over here to this microscope, you can look and see when that Beck line disappears. When the Beck line disappears, you know that the refractive index of the silicone oil and the refractive index of the glass have matched, and you can then assign a refractive index to that piece of glass and use the refractive index to characterize what that glass was actually made of. Of course, you're still going to do this with a standard reference sample. The natural variation is going to be you're going to have more sensitivity to this test than the last test, but it's still not so much that it's going to be a problem for most commercially manufactured glass. So this is an example of the Beck line. Here's that weird like glowy line that you'll see as long as the refractive indices are different. Finally, you can characterize glass by looking at the fracture pattern. So you're going to look at the radial pattern, the concentric pattern, whether the glass splinters or dices, and look for cross transfer of evidence. And you'll also look for stress lines. And we'll show you a picture of the stress lines as the last slide to this. So the radial pattern forms from on the opposite side of the impact. You hit the surface, it bends, you hit something, and then that glass will bend outwards and it'll crack on the opposite side because that's the side that's bending outwards, right? It'll crack on that side. The radial patterns are the ones that go out from the source. Think like the radius of a circle, right? These are going to form on the opposite side of the impact, as I mentioned, and they'll move further with the first impact. So the first time the glass is hit, these cracks will be very, very, very long. For the subsequent hits, they're going to be shorter. The concentric pattern is these circles around that go this way, and they're going to form on the same side as the impact, and they're a byproduct of the radial pattern fracturing. So you have this projectile going through the glass, it bends outward and then ultimately breaks, so you have a crack on that side, but then that ultimately creates a sort of an artificial bend, and the stress will release from the glass on the other side. And those move around in a circular pattern around the impact. Stress marks are going to be shown if you look at the pieces of glass sidelong. So if you look at the piece of the glass, and you see stress marks that'll look sort of like this. For a radial pattern, the stress marks are perpendicular. The perpendicular on that side is on the opposite side from the impact, so it's on the cracking side. And on the concentric pattern, the stress marks are on the same side of the impact. So really, it's wherever the glass had to crack outward facing to is where the perpendicular part of those stress lines will be. This is something you can examine if you find a shard of glass, but you don't know exactly where it would fit into a puzzle of other shards of glass. The initial hole might be asymmetrical on concentrical patterns, but they'll get more regular and more spread out the further away you go from the original impact. Regular glass will splinter, tempered glass will dice. Remember, automobile glass is at minimum all tempered, and some of it is going to be laminated as well. Whenever there's contact, there's going to be cross transfer of evidence. So remember, this is, even though it is hard, it can still retain some properties of whatever went through it. You might get some lead from the outside of a bullet. You might get bullet powder. You can get oils or blood from somebody's skin, if they went through glass, you'll have something else that can adhere or be embedded into the glass that you could look for. You'll want to package up different shards of evidence based on what other cross transfer you might otherwise find. So this is an example of what stress pattern looks. So here's the perpendicular side, and then it comes down. So on a radial impact, if this is pointing to the, if this is a shard of glass on the radial, one of the radial planes, this is the opposite side from the impact. If it were from an angle of the glass that would be affected by concentric fracturing, that would be on the same side.